Now we have to figure out what is the work done by the gravitational force. The gravitational force acting on the ball is the weight of the object, which is mg. So the work done is given by the formula Fs cos theta, where force will be mg, displacement in this case will be the height h, and theta. What will be the angle theta? It will be 0 degrees, since mg is acting downwards and also the ball is going downwards. So displacement is downwards. So the angle is 0. Hence, the work done by mg will be written as mgh cos 0. Cos 0 is 1. And we can write mgh is the work done. Now, let us consider case 2 where the ball is thrown up but from the same point. So, analyze the ball is originally at the same point but it is being thrown up. It reaches a maximum height and then falls back down to reach the final position point B. In this case, if you have to figure out the work done by the gravitational force, so the force will be mg. Displacement in this case too is also h, because the initial point is A, final point is B. Displacement, let me try to label this A to B. This is the displacement, and incidentally that is equal to h. So even in this case, the work done by the gravitational force will also be equal to mgh. Similarly, now let's consider a third case where the ball is thrown at an angle. So let's say the ball is originally in the same position, point A, and then it is thrown at an angle to reach a point which is the same point B. In this case, what will be the work done by the gravitational force? Force is mg throughout the motion. Displacement, even in this case, will be d, because if I connect the initial point with the final point, this distance is also h. And like in the previous two cases, work done by gravitational force again will be mgh. So now you can analyze, as long as the initial and the final points are the same, work done by the gravitational force does not depend on the path taken. It is the same in all the three cases. Now we can deduce that work done by the gravitational force does not depend on the path taken, and by definition, then the gravitational force is called conservative. Now let us quickly distinguish between a force which is conservative and a force which is not. So the next topic is conservative forces versus non-conservative forces. So we have just discussed, in conservative forces, work done is independent of the path. So no matter what path you take, as long as the initial and the final points are the same, work done is always the same. But in case of non-conservative forces, work done clearly depends on the path. So examples of conservative forces which we already discussed, number one was the gravitational force, number two we have spring force, three electric force, and then we have magnetic forces. So all these forces are considered conservative. On the other hand, what are the examples of non-conservative forces? So you need to remember, first is the friction, second we have air resistance, third most importantly applied force. So if you are pulling or pushing an object, that applied force is also non-conservative, and fourth would be tension. So these are some examples of non-conservative forces. Now let me try to explain this using a diagram. So imagine we have a ball over here. Let's say this is the initial point and it is going towards the final position. Case 1, the ball is going in a straight line along this red arrow. And let's say the work done by the ball while it is following this path is, let's say, W1. So this is case 1. Case number 2, the ball is traveling from the initial to the final point but along a different path. So have a look. The path becomes irregular. So the initial and final points are the same, but the path taken is definitely different. So in this case too, let's say the work done is W2. Now let us consider the third path. The object reaches the final position and let's say the work done in case 3 is W3. So according to the definition, if the forces involved are conservative, all the work done will be equal. So work done is independent of the path. That is the definition of conservative. On the other hand, if the forces involved are non-conservative, then the work done will of course be different. So W1 is not equal to W2, not equal to W3. So in the exam questions, it will be very crucial for us to figure out what is the work done by a particular conservative force. And that is the next title, work done by conservative force. So the formula is simple. WC stands for the work done by the conservative force. Delta U is the change in the potential energy. Change in potential energy is final minus initial. So if we combine the expressions, we will get WC, work done by the conservative force, equals to negative delta U, which will also be equal to initial energy minus final energy. And why we have placed initial in the front? Because of the minus sign. So let's say if the question asks us to find the work done by the gravitational force, so the formula becomes work done by the gravitational force, which is mg. Work done by mg will be equal to negative of change in the gravitational potential energy. So the formula becomes this, and gpe initial minus gpe final will give us the work done by the gravitational force. After this, let us consider spring forces, which are also conservative. So, work done by spring forces will be equal to negative of change in the elastic potential energy. So, let's write work done by the spring force will be negative delta EPE, which is equal to the initial elastic potential energy minus the final elastic potential energy. And now let us try to solve a question based on these principles. So here we have an inclined plane on which a box is kept. So the question is, what is the work done by the gravitational force acting on the box as it moves up the incline from point A to point B? Now the question has specified that we need to find the work done only by the gravitational force which is acting downwards. Now there are two ways to solve this question. Method number one, we are going to use the basic formula work done by a conservative force is equal to negative of change in the potential energy. In this case, the force is gravitational, so we will write down the formula work done by this gravitational force mg will be equal to negative of the change in the gravitational potential energy, which can then be written as gpe initial minus gpe final. Initially the box is at point A, and since the point A is on the ground, we can assume the gravitational potential energy of the box at the point A to be 0. So initial GPE will be 0. And finally, the box reaches point B. There, the formula for GPE we can use mgh, where the height is 1 meters, as you can see in the diagram. So over here, we will write initial GPE is 0, final GPE is mg into 1. And if we simplify this, we will get negative 20 as the answer, because the mass of the object is 2 and g is 10. So work done by the gravitational force as it is going from A to B will be negative 20 newtons. So this is the first way of solving this. Now the second method, we are going to use the basic formula for work done, which is F into S into cos theta. Now we also know work done can be written like this. Work done is the product of force with component of displacement along the force. Now, if you analyze this image, although the box is going from A to B, that is the overall displacement AB. But what is the component of displacement along the force? Now, the force mg is vertical, it is along the y-axis. So, we have to find the y component of AB, which will be CB. Now, if we understand the total displacement, the object is going from A to B in a straight line, but in component terms, we can say that the object is going from A to C along the x-axis, and then the box goes from C to B along the y-axis. Now, since we have to find the component of displacement along the force, that component is BC, which is 1 meters. And then we can write this expression as force is mg and the component of displacement is CB. And why we have put a negative sign in front of this formula is because the force mg and the displacement are in opposite direction. So if you analyze this image, mg is downwards, the object is going from C to B along the y-axis, so CB is up, mg is down, and that is why we have put a negative sign. And that's it. Let's put the values in. M is 2, G is 10, and CB is 1 meter. So if we simplify, we will get negative 20 newtons as the answer. So in an exam scenario, depending on which method you prefer, you can use any method. But generally, this method 1 is preferred because there we don't have to deal with any components. All right, so now back to the logic. Whenever we are applying the conservation of mechanical energy, we need to be careful about certain conditions which needs to be satisfied. Condition number 1, which we discussed, the system should be isolated, which means the net force acting on the system should be 0. And number 2, all the forces acting on it should be conservative, which means forces like friction, air resistance, applied force should not be there. So if a non-conservative force like friction acts on the system is going to lose energy. For example, in the form of thermal energy. So in that case, mechanical energy will not be conserved. So while solving questions, we need to be careful about the presence or absence of non-conservative forces. So again, consider we have a block which is kept on an inclined plane and it is sliding down this incline and finally reaching the bottom of the incline at the final velocity v. So according to the law of conservation of mechanical energy, initial energy will be equal to the final energy. But do remember, you have to apply this equation only if friction is absent. So let's see, use mechanical, remember this as a rule. So use mechanical energy conservation only if conservative forces are present. If non-conservative forces are present, for example, friction, in those cases, the approach is a little